Ancients couldn't understand lightning, stars, diseases, magnetism, or even ourselves. The world seems to be full of mysterious things, powerful forces, and strange animals, which are beyond human comprehension. In recent years, this confusion has been replaced by a strong confidence. We think we understand the world around us, for the history of mankind is quite new. Basically, in your daily life, meet very mysterious things. You have hardly seen things that you think are completely unexplainable. Lightning, or stars, diseases, or magnetism. You know that behind these things are natural laws. These things themselves are very complex and awe-inspiring, but they are all constrained by physical laws. In fact, the experience of confusion and no explanation is very precious. We'd rather spend money to experience it again. That's why magic shows are particularly interesting. Besides understanding, we can also control the things around us. We can regularly let a 400-ton plane fly across the ocean. We can control the quantum mechanics effects, the quantum mechanics effect of billions of transistors. We can cut open the human body and implant organs. Actually, if you think about it carefully, we really live in an era full of miracles. We are so good at explaining the big trends and small details in the real world. Does this mean that we already know everything? Can our theories explain everything? You should have already thought of the answer. Of course not. Through our program, you already know that there are still too many things about humans that have no answers. We know very little about things that are everywhere in the universe. That is, dark matter, and super energy, and dark energy. We know almost nothing. Our control only exists in a small corner of the universe. We are surrounded by the vast and ignorant sea. We have to face this fact. We understand the world around us, but know nothing about the universe. How far are we from discovering the ultimate theory, the theory of everything? Is there such a theory? Can it explain all the mysteries in the universe? All the mysteries? To discuss this question, we need to talk about the theory of everything. In short, the theory of everything is the most thorough and all matter in the universe, all energy and all forces in the most thorough and simplest mathematical description. Let's analyze it. The definition includes matter, because this theory must be able to describe everything that makes up the universe. It also includes forces, because we don't want this theory only describe inert masses of matter. We want to know how matter interacts with each other and what the laws of nature can do. It also includes space and time, because we know that these two concepts are to some extent extensible and affect matter and forces in the universe. They are also influenced by matter and force. Most importantly, we need this theory to be very concise and profound, because we hope that it can give the most essential and reasonable description. It should be a concise and essential outline. In other words, it should use as few variables as possible and as few unexplained constants as possible. And it should be able to describe the entire universe. We want to find the smallest building blocks that make up everything. We also want to know the most fundamental mechanism. What is the most fundamental mechanism? Look, we live in an onion-like universe. In this way, because it is composed of many different layers. For example, atoms have a nucleus composed of protons and neutrons, and electrons revolving around the nucleus. You can see that many places draw such a picture, which is a circle in the middle, and many small balls around it. This may be the most well-known scientific model. Many places use this image to represent science. The proposal of this model is an extraordinary achievement. We say that not only because the model itself is famous, but also because it means that human beings no longer regarded atoms as the basic unit of matter, which means that humans have understood a deeper truth. Matter may be composed of smaller parts. That's not all. Among these parts, smaller than atoms, some of them are actually composed of smaller parts. For example, protons and neutrons are composed of quarks. Not only that, at this scale, the way particles move are completely different from what we expect. The facts are very different from our imagination. Electrons, protons, and neutrons are not gathered together and surround each other, but small spheres with hard surfaces. They are defined by waves and governed by uncertainty. They are blurry quantum particles. However, these views only hold to some extent. You can say atoms are like billiard balls, which helps you understand how gas atoms collide and bump in a container. You can also say atoms are tightly packed particles surrounded by electrons. This one helps you understand the elements in the periodic table. The new quantum particle view can explain various natural phenomena very well. The key is that in the universe we live in, many theories can indeed work without paying attention to small scales. To work In other words, you can accurately predict the collective behavior of all the small parts, even if you don't know what each small part is doing. You don't even need to know whether these small parts really exist. Let's take an example. Economic research can describe collective behavior, but economists don't need to analyze the psychology of each individual. The behavior of many shoppers and merchants determine the macro changes in prices. This can be described by several equations. You can study and describe the economic behavior of a group without knowing the choices of any individual and motives. There are many such examples in physics. For example, even though we haven't discovered the most basic unit of matter, and we still don't know gravity works in the quantum theory system, we can still accurately predict what will happen when a baboon jumps from the roof. What will happen? Newtonian mechanics can predict the parabolic motion of baboons. Fluid mechanics can tell us about the splashing of water. Biology can explain what happens when the baboon falls into water. What will happen? In fact, theories in the universe are also layered. Before we understood DNA, we already had evolution. Before we knew about Higgs boson and other particles, we had already sent humans to the moon. This is very important because the ultimate theory, such as that has haunted all physicists, it will actually describe the most fundamental core of nature. This ultimate theory will not describe high-level phenomena, but the basic components of the universe and its own constituent mechanism. This makes the concept of the laws of nature become somewhat subtle because we may never be 100% sure. We already have such a theory that seems very basic to us. There may be another layer of the universe onion behind it. How can we distinguish the differences? What's worse, if the universe has infinite layers, what should we do? Could the ultimate theory simply not exist? Since we have defined the laws of everything, let's talk about, in the process of human understanding of nature, the deepest progress it has made. One question we can ask is whether there is the smallest distance in the universe. In our daily life, we are used to thinking of distance as something that can be infinitely divided. Between 0 and 0.001, you can find an infinite number of distances. But what if this is not the case? If at a certain critical point, shorter distances would lose their function and meaning? What if the real world is like the pixels on a screen? What would happen? So, once we describe objects on this scale, and the interactions between objects, we can think that this theory is the most fundamental, because there will be no smaller things. However, if there is no such smallest distance, if things can be infinitely small, or can move at infinitesimal distances, then we will never be able to determine whether there are other theories at the next level. Another way to solve this problem is to think about this question. The objects we want to describe, are they really the most fundamental? We have discovered electrons, quarks, and other particles. Are they the smallest particles in the universe? Are there any smaller particles? There is another last question. How these objects interact with each other. They have many different ways of interacting, such as forces, or only one way of acting, but they just manifest as different forces. Is there a most fundamental description in the universe that can summarize all forces? You see, we have thrown many questions to you at once. You can think about them together. Let's start with the first question, the smallest distance. Whether there is a minimum distance in our universe, or the smallest resolution, in other words, is whether our real world is pixelated. Let's spend some time thinking about it. If the real world could be pixelated, how strange this idea would be. Quantum mechanics tells us that we cannot absolutely know the exact position of a particle. That's because the objects studied by quantum mechanics are random. But in addition, quantum mechanics also tells us that the exact position of a particle is uncertain. Beyond a certain limit, at smaller scales, the position information no longer exists. This is a clue. There may be a smallest meaningful distance. We might think of this quantum distance as pixels. But if the real world is pixelated, how small these pixels are, we really don't know. Physicists have been searching everywhere and combined several basic constants about the universes to combine them and made a rough estimate. Among these constants, there is the Planck constant h in quantum mechanics. It is a very important number because it is related to the basic quantization of energy. You can think of it as the pixelization of energy. To obtain a number that can define distance, physicists use the Planck constant to multiply by two other constants. These two constants are the maximum speed of the universe, which is the speed of light c, and the strength of gravity, and the capital G. Combining these constants in a specific way, we can get a number representing the unit distance. This number is very, very small. Only 1 10 to the minus 35 meters, which is 0 followed by 35 zeros. We call this number the Planck length. What does it mean? We don't know exactly, but it may give a rough estimate of the pixels of the universe. Combining these numbers together doesn't make much sense, but each of them represent the elements of quantum physics. So when combined together, they may provide clues about the basic scale of the universe. Clues about the basic scale of the universe. The answer is no. Our tools for exploring small distances have developed from optical microscopes that detect visible wavelengths to electron microscopes. This electron microscope can detect matter on the scale of about 10 to the minus 10. Detect matter. In addition, high-energy particle colliders can observe the internal structure of protons. Unfortunately, it means that we are still far from verifying the truth of the Planck length. It's still 15 orders of magnitude away. That is to say, we are likely still unable to understand many details. How many details will be missed by 15 orders of magnitude? You can imagine that if the smallest ruler you have, or the smallest thing your eyes can see, is 1 meter long, which is 100 times the width of the solar system, you must be ignorant of things smaller than this scale. Be ignorant of. That is to say, the smallest scale of the universe we can observe. Now, if it is the size of the solar system, all things in the solar system, we can't detect them all, because it is too small for us. On the scale of 15 orders of magnitude, you will miss many, many things. Do we still have hope to explore the truth of things? Explore the truth of things? The technological progress of this world, in 100 or 200 years, has taken us from the world under the optical microscope, 1/100th of a meter world under an optical microscope, to the quantum colliders, to the world of 10 to the minus 20th meters. It's hard for us to predict what future scientists will be able to show us. However, if we infer from the way quantum colliders are used to make inferences to see something at the Planck length, the energy of the accelerator will be 115 times higher than 150 times higher. Unfortunately, to meet this requirement, both its size and its cost will also increase by a factor of 10 to the 15th. So many times 10 to the 15th is really unbearable. We have no hard evidence of the pixelization of the universe. However, quantum mechanics and the cosmological constant we have detected so far strongly suggest that there is a minimum distance in the universe. Of course, this distance must be very, very, very small. After we talk about the smallest distance, let's talk about the second idea. The smallest particles, the electrons we have discovered, quarks, and other elementary particles, are really the most fundamental particles in the universe. It's very likely not the case. Electrons, quarks, and all their expressions seem to be emergent phenomena of something. Perhaps they are just smaller and more basic particles, or a cluster of particles. The reason why we think so is because all the particles we have discovered so far can be found in a table that looks like the periodic table. Find their place. When we talked about quarks before, we told you about this table. If you forget, you can go back and listen to it. If you don't know, you can just think of it as an element periodic table about quarks and leptons is enough. This neat arrangement and the patterns within it, it tells us that behind all this, there must be something else at work. Scientists found clues from the periodic table of elements and found that all elements are combinations of electrons, different combinations of protons and neutrons. This table makes physicists suspect that these particles are probably composed of some smaller particles, which may involve some unknown laws or rules, or laws. Anyway, the clues are there. How do we know what lies between electrons and quarks? We need to let various things keep colliding with each other. If a particle is a complex particle composed of smaller particles, then these smaller particles must be bound together, constrained by a binding energy to bind them together. For example, a hydrogen atom is actually a proton, and an electron is formed by electromagnetic force. And the proton is formed by 3 quarks through the strong force. If you use energy lower than the binding energy to hit a composite particle, then the composite particle will behave like a solid particle. For example, a monkey holds a baseball and throws it lightly at you, and you will see the ball bounce off, and your car is unscathed. In the monkey's eyes, your car is a hole. But if the baboon holds a stone, throws the stone at your car very hard, the energy carried by the stone is higher than the energy that maintained them together is higher. Then it will knock off a piece of the car. You will see that your car has smaller parts. So to know whether electrons and quarks are composed of smaller particles, is to give them higher and higher energy and collide with each other. If the collision energy is higher than the energy that keeps electrons and quarks together, higher, they will be broken apart. We will know that they are composed of smaller parts. But we actually don't know electrons and quarks are composed of smaller parts. Even if they do have smaller parts, we don't know how much energy is needed to break them apart. So far, our colliders don't have enough energy to find particles smaller than electrons, quarks, or their cousins that are smaller. There is another way. We may be able to calculate to obtain some laws of the periodic table of particles and find new particles that can be filled in the table. If we find more cousins of electrons and quarks, we may be able to infer the pattern in this table and find more clues about the deeper structure, just like what we did to the periodic table of elements. This may tell us whether there are smaller particles are hidden in our existing particles. Having talked about particles, let's talk about the most basic forces. The last piece of the puzzle in building the laws of nature, the description of the basic forces in the universe. We know that matter particles interact with each other in several different ways. But how many forces are there in total? Could they be different parts of the same phenomenon? Finding the most fundamental description of forces in the universe. It's not about strength. The key is to find out which forces we know are the same thing. For example, if you ask an ancient person to tell you what forces exist in this world, he might write a long list. In this form, might include the force that made me fall off a horse, the force that moves the big ball of the antenna, the force that breaks branches, the force that the mammoth stepped on my toe, the force that makes fish swim in the water, and so on. But over time, scientists gradually understood that many of these forces are interrelated. The content in this table can be summarized into several types of forces. We know that the force that makes people fall off horses and the force that makes the big ball in the sky, the sun moves, are actually gravitational forces. We also know that when branches and elephants touch each other, the force that acts on them are the same force. That is the force of atoms approaching each other, repel each other. The electromagnetic unification theory emerged in the 19th century. We have talked about James Clerk Maxwell before. This great man, he discovered that current can produce magnetic fields and moving magnets can generate electric current. Therefore, he wrote down all the known electromagnetic equations, including Ampere's law, Faraday's law, Gauss's law, and so on. Later, he discovered that they were completely symmetrical. Electricity and magnetism can be regarded as one concept and describe them in another way. Electricity and magnetism are not two different things, but they are actually two sides of the same coin. The same. Some recent events have been reenacted in the weak nuclear force and EM force. Two seemingly different forces are found to be two sides of the same coin. Similar mathematical descriptions can be summarized as the same force. This force is called weak force. Behind the photon that we are all familiar with, there's a deeper force behind it. This force can generate W boson and Z boson. What about the W boson and Z boson? Are the particles that transmit the weak nuclear force. Well, the current state of reality is that we have reduced the long list of forces, about forces, to a very short list. There are three things on this table. The first one is weak electricity, and the particles that transmit it are photons, W bosons, and Z bosons. The second one is the strong force. The particle that transmits this force are called gluons. The third force is gravity. The particle that transmits it is called graviton. However, the graviton is only at the theoretical stage. So, how much can we reduce the number of forces? To what extent? Is it possible that all these forces, essentially the same force? The current answer to this question is 3 words. I don't know. After we talked so much just now, the law of all things, in the simplest and most basic way, describe everything in the universe. This means that, as long as the smallest distance in the universe exists, the law of all things can be established at this smallest scale. It must include the smallest volume in the universe into its jurisdiction. It must also describe all the interactions, all possible interactions, which is force. So far, we have some clues and ideas about the smallest distance in the universe. We have a nice table that includes 12 types of matter particles. These particles cannot be further decomposed. We have also summarized the 3 possible interactions of these particles, which are the weak force, strong nuclear force, and gravity. So how far are we from the theory of everything? Of course, the answer is unknown, but nothing can stop us from making bold guesses. Judging from the current trend, for the matter, forces, and space in the universe, we may eventually obtain a theory that describes and one force. It may point out the smallest pixel in the universe, or prove that this pixel does not exist. With this theory, you should be able to peel off every layer of the universe, explain everything with one force and one particle. It seems that we still have a direction. Remember, all the theories we have mastered so far only cover 5% of the universe. We told you this in the first episode of our album. So far, we still don't know how to understand the remaining 95% of the universe. Regarding the theory of everything, there is another rather vexing problem, which is how to combine gravity with quantum mechanics. This is a major obstacle to our pursuit of the theory of everything. Let's talk about this again. Originally, for the universe, we have two theories, to be exact, the theoretical framework. They are quantum mechanics and general relativity. In quantum mechanics, everything in the universe, even forces, are quantum particles. Quantum particles are tiny disturbances of entities. Because they have wave-like properties, so they have inherent uncertainty. These perturbations move around at some level in the universe. When they interact with each other, they exchange wave-like particles. Currently, we have quantum theories of strong and weak forces, but there is no quantum theory of gravity. On the other hand, general relativity is a classical theory, which means it was proposed before quantum mechanics. It does not assume that the universe is quantized, nor does it assume that matter and information are quantized. However, general relativity is very good at modeling gravity, which means calculating gravity. In general relativity, gravity is not a force, but the curvature of space itself. When an object has mass, it distorts the surrounding spacetime, making everything nearby all bend towards this object. In this way, we can explain most of the fundamental forces, the great particle theory, which is quantum mechanics, and the theory that explains gravity, general theory of relativity. But the problem now is that these two theories are incompatible. If we can somehow integrate the two theories together, that would be great. In that case, we can get a universal theoretical framework from which we can build a theory of everything. Unfortunately, this has not been realized. It's not because scientists haven't worked hard enough. When physicists tried to combine quantum mechanics and general relativity together, two major problems arose. The first problem is that quantum mechanics seems to only work in a flat, uncurved space. If you try to apply quantum mechanics to work on gravity in curved space, strange things happen. At first, in order to make quantum mechanics meaningful, physicists had to apply a mathematical technique. This technique is called renormalization. This technique allows quantum mechanics to handle some strange problems, such as point particles, electrons, radioactivity, and density. Problems, and the infinite number of low-energy photons emitted by electrons. Problems, renormalization. Physicists can sweep these infinite problems to sweep them under the carpet, pretending everything is okay. But unfortunately, when scientists try to apply renormalization to the quantum theory of gravity in curved space, it doesn't work. Of course, there are deep mathematical problems involved, which we can't explain. In short, in such an environment, no matter how much you try to hide, there will be an infinite number of problems waiting for you. That is to say, the current quantum gravity theory, this quantum gravity theory combines quantum mechanics and gravity theory. This theory always gives crazy predictions involving infinity. This means that they cannot be tested. What do scientists think about this? Is that gravity has some kind of feedback effect. The more space bends, the stronger the gravity, the more mass it attracts. The feedback effect of gravity is, of course, nonlinear. As we mentioned earlier, in the quantum description of weak and strong forces, there is no such situation, because the space they are in is flat. After listening to this description, you may be a little confused. This is actually what we said earlier. For ordinary people to study physics, we can only watch the excitement. Once it comes to more profound knowledge, you don't know math, you can't even read the questions. What we just said. In layman's terms, when we integrate general relativity and quantum mechanics, the first problem we encountered was actually a mathematical one. The direct result is that our existing theories cannot be used for calculation. The second problem in integrating general relativity and quantum mechanics, the second problem is what? It is not a mathematical problem, but a philosophical one. These two theories have very different views on gravity. If we want to incorporate gravity into quantum mechanics, we need to find the particle that transmits it. But no one has ever seen such a particle. Strictly speaking, until recently, have mastered the technology to detect such particles, and we haven't detected them yet. This issue, we have a special section earlier. When we talked about the mysteries of gravity, we have explained in detail. You can go back and listen to it. Based on these two reasons, These two theories describing the operation of the universe are difficult to integrate. We don't even know whether they can be integrated. We don't know what the graviton will look like. The theory of quantum gravity fusion always makes infinite tendency, meaningless predictions. Perhaps we haven't found the mathematical tools that really suit the integration. Maybe our method of fusion is problematic, or both. We know how to calculate forces in quantum mechanics, but we don't know how to use it to calculate the curvature of space. So how can we know when we have succeeded one day? Now, let's assume that scientists have successfully built a particle accelerator as large as the solar system and thereby obtained the Planck length, which is the smallest meaningful distance element of the basic substance. We can imagine that once we master the elements of this substance, we can explain the basic quantities of these substances, how they interact, and jointly form natural phenomena on a larger scale. If we really achieve this, does it mean that we have achieved our goal? You may have heard of Occam's razor, which says that if two theories can explain the same thing, the simpler one is more likely to be correct. Physicists have always been lucky. They always discover the same essence behind different phenomena and successfully simplify the theory. This is also the reason why they despise other disciplines. We can ask if there's the most concise theory, just as we can ask whether there's the smallest particle. We may prove that there is the smallest distance in the universe, or the smallest particle. However, can we prove that there is the most concise theory for everything? How can we know we have achieved the greatest success? We may think we have succeeded, only to find alien physicists have a simpler theory. We first need to consider how to measure the simplicity of a theory. What kind of theory is a simple theory? Does it mean the shorter the formula, the better? An important criterion is the number of numbers. Suppose you have come up with a theory of everything, and there is a number in your formula. Regardless of what the number is, anyway, it is important. Let's make a random assumption. Let's say it is the mass of the most basic particle, the neutrino. Moreover, people must know the specific value of this number. To apply this theory, then you naturally think of the one we just mentioned, the collider, as big as the solar system, to measure the mass of neutrinos, and then bring this value into your theory. In this case, your theory is completed. You think you have found the most concise theory, but at this time, another person appears with another theory of everything. His theory is slightly different from yours. His theory derives the exact value of the neutrino mass. This value must be an exact number, otherwise the theory would not hold. He doesn't need to measure this value because this value is calculated by his equation. In this way, his theory is better than yours. One less artificial variable. Your equation may appear more concise than others, but his equation reveals more information about the universe. This is because his equation will tell us why the neutrino mass must be that value, while your theory can only measure the mass of neutrinos manually, but you don't know why the mass of neutrinos is that value. So this person's theory involves fewer numbers, which means it is simpler and more fundamental. Through this hypothetical example, I hope to illustrate this point. To know if we have found the truth of everything, there is a way to counting how many artificial numbers this theory involves. The fewer such numbers, the closer we are to the center of the onion. Maybe there are no numbers in the center. Maybe the essence of the universe is an amazing mathematics. All the numbers we know, such as the gravitational constant, Planck length, can be derived from this theory rather than measured. Currently, there are many parameters in the standard model. Parameters in the standard particle model is the one we are using now, the most widely used particle model, which includes 12 parameters used to describe quark and lepton masses, 4 parameters that determine quark conversions, and 3 parameters that determine the strength of weak force, and 2 parameters for the Higgs theory. Counting them, there are 20 numbers in total, without involving gravity, dark matter, or dark energy, and we can only use these 20 numbers, but we don't know why they are these values. In fact, we don't know how to judge whether a theory is the law of everything. No one can say for sure whether the numbers in the universe are random. If one day we finally discover the law of everything, there is only one parameter in this formula. The number is 4. We may ask why this number must be 4. The basic number may have been randomly set in the early universe. In other universes, they may have different values. You should be careful. Most of these views are contrary to the falsifiable scientific hypothesis, because you can't verify it. It is already in the realm of philosophy. Since we are still 15 orders of magnitude, by 15 orders of magnitude, then we might try another method. This method is that we don't go through each layer of the onion and drill down layer by layer, but start directly from the center. What is the result? The meaning of starting from the center here. That is, we don't start from 10 to the minus 20 to detect 10 to the minus 21st power. We don't look for particles one level smaller than quarks, but directly assume there's the smallest particle, even larger than quarks, is 10 to the 15th power larger than it. Such a large order of magnitude. As long as the laws of nature you propose can ultimately explain the particles we see today, from a technical point of view, your theory is unassailable. There are many theories that make direct assumptions. The most famous one is string theory. In modern physics, string theory is probably the most popular and the most controversial theory. It suggests that space-time in the universe may have 10 or 11, or even more. These dimensions, we can't see them because they are either curled up or very small, which are filled with tiny strings. These strings are vibrating because there are many ways of vibration, so they can behave very similar. We have discovered any kind of particle. They can even explain particles that we haven't discovered yet, such as the graviton. What's more, string theory is considered to have mathematical beauty and theoretical beauty. String theory is a true theory of everything because it unifies all forces, describes the real universe at the most fundamental level. However, there are still several problems with string theory. These problems are quite serious. Firstly, despite the hope that string theory can describe the entire universe, it has not been able to do so completely. Its mathematical methods are still being improved. Before it can be regarded as a complete descriptive theory, there are still some parts that need to be implemented. Second, string theory is just a descriptive theory. It cannot make any predictions that we can test. In order to let people know the smallest unit of the universe is a particle or vibrating string, every theory must make testable predictions. Because string theory is currently only studied length, we can't study objects. We can't test it. Because we can't detect with that high precision. In this case, whether to believe in string theory, it is a philosophical mathematics, and even a matter of faith, rather than a physical problem. Of course, one day in the future, more advanced experimental techniques and smarter physicists may find a property of the universe. And this property exactly matches the predictions of string theory. In this way, string theory will be verified. Of course, this has not yet become a reality. The last puzzle about string theory is about parameters. The dynamics predicted by string theory is determined by the number and shape of space-time dimensions. There are many ways to choose. How many dimensions are there? Is 150. Obviously, so many possibilities are too outrageous. Further formalization of string theory is expected to narrow down this number, but it still has a long way to go. So, up to now, we can only say that string theory is the most beautiful in math. In terms of possibilities, we have no better choice. But if someone tells you that string theory has become the ultimate theory and has explained the universe, explained without any problems, you must not be fooled. So in this section, we have spent so much time talking about this ultimate theory. The most important thing is to dispel a misunderstanding. When answering questions related to daily affairs, the theory of everything is not very useful. Even if the theory of everything can reveal the universe's, the inner working mechanism at the most basic level, it is likely to be useless in practice. We said before that the universe is like an onion. Every time we go up a layer, there is a phenomenon called emergence. What does emergence mean? Let me give you an example to understand. For example, the television we watch is composed of small pixels. We won't discuss it in depth here. What kind of television is used? Let's assume that each pixel is a small light. Now you have such a formula that can accurately predict which color, at every moment, which color it will light up, red, yellow, or blue. In this way, using this formula, at the micro level, you can accurately predict the state of each light. However, no matter how accurately you predict the state, you won't know what program is being broadcast on the television. If you want to know what's on, just step back a little. You can tell by just taking a glance. Or the weather forecast. This phenomenon from the bottom to the top is called emergence. In real physics, when you want to describe the movement of a bouncing ball, you can use the Newtonian mechanics you learned in high school, treat the entire ball as a force-bearing object. In this case, you can draw a simple parabola and use a line of mathematical formula to describe it. Of course, you can also use quantum field theory to describe the ball. For the 125 particles that make up the ball, to model quantum mechanics and track when they interact with each other and the environment, what happens. This makes sense in principle, but it is not practical in practice. Theoretically, the answers obtained are also correct. However, mathematically, we can't complete this task. If there is a correct theory about the underlying reality, then in theory, we can get all the knowledge from it, from the formation of galaxies to fluid mechanics to organic chemistry. But in fact, this is simply a fantasy, and this is not how science works. No one would expect a surfer to understand string theory and calculate how many particles are moving in it to help him stand up on the surfboard when cooking. You wouldn't want to get a recipe written in quarks and electrons. If early scientists had to start with the most basic particles, we would have made no progress at all. So, you can actually understand it this way. Searching for the theory of everything is an obsession exclusive to physicists. In this process of searching, humans have been working hard. What they want to obtain is not that this theory can guide who to cook, but to reveal the deepest and the most fundamental truth. Humans are good at systematically describing the world. From chemistry to economics to psychology, we use many scientific descriptions to improve life, treating diseases, or getting faster internet speed. These descriptions are not basic enough, but only describe emergent phenomena. However, this does not affect their practicality and effectiveness. We just can't get from these theories the satisfaction of revealing the true mechanism of the universe. We want to know the deepest truth. It's not because it can help us do something, but because we must know why. Today, we talked about many obstacles to finding the truth, but these obstacles can't convince us to stop searching. Whenever we uncover another layer of truth, whenever we move towards the center of the universe, we take another step. Novel structures will appear before us. It makes us have our way of existence. Perhaps this is the biggest difference between humans and other creatures. Well, that's all for this episode. Let's continue our conversation next time.